Good afternoon to everyone, to all participants. Welcome to our webinar talk today, where the title of our webinar for today it's on polyurethane flatbed, an ingenious solution to resolve settlement on soft soil ground. So the webinar today will be given by our speaker, Engineer Dr. Ismail Syahadi Bagus Muhammad Jais. So before we start, let me introduce his background. Engineer Dr. Ismail Syahadi Bagus Muhammad Jais obtained his bachelor's degree in civil engineering, University Teknologi Mara, Malaysia in 2001. He then obtained his master's degree in geotechnical engineering, engineering geology from University of Newcastle upon Tyne, United Kingdom in 2004, where his dissertation specializes in finite element analysis of geotechnical problems relating to Malaysia in 2001. He then obtained his master's degree in geotechnical engineering, engineering geology from University of Newcastle upon Tyne, United Kingdom in 2004, where his dissertation specializes in finite element analysis of geotechnical problems relating to more trial embankment using PLAXIS finite element code. He finally obtained his PhD in civil engineering from University Teknologi Mara, Malaysia in 2014. Focusing on wetting collapse behavior of saturated and unsaturated soils. He is a professional engineer with the Board of Engineers Malaysia and member of the Institution of Engineers Malaysia from 2021. His interests include numerical modeling of geotechnical problems, geoforensic engineering, alternative ground treatment and ground engineering, slope engineering and rehabilitation, embankment dam engineering and tunneling. Currently, he is a senior lecturer in the Faculty of Civil Engineering UiTM and has involved in research and consultations relating to numerical simulation and physical modeling of geotechnical problems. His project include assessment of tilting retaining wall in Semenyih for Kasmet Sdn Bhd, temporary geotechnical support structure at Pulau Indah for TH Heavy Engineering Berhad, stability assessment of new bulkhead and wharf at Pulau Indah for TH Heavy Engineering Berhad, detailed design of ground repair and remediation at MTBE Petronas Chemicals Gebeng Kuantan for Petronas Chemical Berhad, dam stability analysis at Wadi Al Asla Jeddah for the government of Saudi Arabia, ground rehabilitation and approach treatment at various JKR plus Expressway Berhad, SKBE Holdings Sdn Bhd and MTD Prime Sdn Bhd project. He's also involved in the MS 2038 Malaysian Code of Practice for site investigation with Standards Malaysia, Standard Specification for Roadworks JKR, Section 18, Soil Stabilization, Section 2, Earthwork, Section 20, Ground Improvement, and Section 10, Piling Works and Construction, CIDB, for guideline in best practices for subgrade stabilization. He has also served with Bahagian Pakar and Forensik Cawangan Kejuruteraan Geoteknik CKG Jabatan Kerja Raya Malaysia as advisor for geoforensic investigation and solution. With that, I will pass the session to him to start the webinar.
Okay, thank you, Dr. Nur Hazwani, for the kind introduction. Assalamualaikum and a very good afternoon to everyone. Okay, I hope all of you are in great shape after a heavy lunch today. So this is a challenging task for me to actually ensure that most of you are wide awake and not falling asleep, okay, during the webinar. So, okay, today I'm going to have a knowledge sharing session with all the participants here on what we have done, research that we have conducted together with JKR and also CREaTE JKR Melaka, where we introduce a solution to reduce the effect of settlement of soft ground, right, on road embankments and also on the transition section between the bridge approach or the pile embankment to the earth fill embankment, right? Okay, so I've actually presented this paper in the International Symposium on Practical Applications of Ground Engineering for Embankments on Soft Soil, which occurred in the on the 18th to 20th October 2022 at Doset Grand Subang. Okay, so these are my co-authors. Yeah, I have Dr. Ismail Abdul Rahman. He's uh, the head at JKR Melaka, right? And then we have Mr. Samsul, Engineer Samsul Amri Muhammad Ishaq, okay, currently with JKR, and my previous PhD student, Dr. Diana Cheklat, right? She has done a lot of the laboratory works, right?
Sorry,
So,
sorry, doctor, to interrupt.
yeah,
Sorry, doctor, to interrupt. Are you presenting your slide?
yes,
Because
uh,
I cannot see. I'm not sure for the participants whether they can see your slide or
okay,
not.
all right, I
Yeah.
already shared my slide. Okay,
Okay. Okay.
okay, so sorry. All right, okay, so this is the paper that I presented, and okay, right. So before I start this session, I would, of course, would like to thank UITM, Shalam, and also Pasigudak with this assistance on providing the test specimens and also on the testing equipment and instruments. And then, of course, JKR Melaka CREaTE for providing the research grant together with CKG, Chong and Geotechnical. So we have conducted this in order to find a practical solution, right, to resolve this certain issue. And finally, of course, the installers of Jocon Malaysians never had. Initially, they did a lot of work in PU injection. So when we start off this research, we have to get another collaborator from industry supplier to actually produce this material and also install it, okay, on site. And of course, not forgetting the valuable individuals that are involved in this research. They provide a lot of ideas and also material for the proposed work. Okay. Right. A little bit of the background. You look at in the Semenanjung, Malaysia, right? This is Malaysia. You can see there's a distribution of soft ground, right, on the coastal areas, and then where in Sabah, Sarawak, you have a peat soil, okay, close to the coast, and basically, in Malaysia, we have problems in terms of construction on soft ground because we have uh, settlement, okay, because the ground is soft, so it does have soft to very soft shear strength, underage shear strength, so the resistance is quite low, right? So it is always prone to consolidation, right? Consolidation settlement. Even though we have constructed the road, we have surcharged it, and then we have filled the embankment to provide a proper platform for the level. However, you still have continuous settlements after it is in service, especially when you have transition section between the bridge to the earth embankment or the pile embankment approach to the earth embankment. So, to understand the behavior of soft clay, the concept of consolidation has always been the key, right? So we want to come out with ideas to resolve the excessive settlement that the soil experience when you have overburden pressures. So basically, in consolidation, as you load, it will generate the excess pore water pressure underneath the embankment. So from there, it will actually cause dissipation in time due to the hydraulic conductivity or the coefficient permeability of the clay very low, so you have a slow dissipation until it reaches 90%, where at this time it is termed as primary consolidation, where the excess pore water pressure dissipates until it goes back to the hydrostatic pressure. Okay, so this actually causes volume change in the soil. So how do you want to actually tackle this problem? We have so many types of ground treatments, ground improvement. We have geotextile, geogrids, high strength geotextile to actually provide reinforcement to the embankment. And then you have vibro compaction, vibro replacement, which is either stone columns or sand columns, right? And then you have chemical injection. For example, you have um, grouting, okay, cement grout, and then you also have jet grouting, right? And then chemical columns and so forth. So there are so many systems. In fact, there are also lightweight system known as EPS, expanded polystyrene system, which actually reduce the effect of the overburden to the soft clay. So some of the baseline in selecting solutions, we consider the salt type, right? We look at this clay and then its engineering characteristics, and then the area depth and location of the treatment required. So we look into the site investigation report to determine how deep you want to actually stabilize or we want to improve. And then site location, which can also influence the selection when dealing with the existing surrounding. That means access to site, right? The environmental surroundings and whatnot. And then, of course, soil properties, look into the compressibility characteristics and also the shear strength characteristics of the soil, right? Don't forget, you also have permeability. So you want to look at the rate of consolidation or the coefficient of consolidation as well. And then the availability of the materials, okay, site, skills and local experience of the contractor, the environmental concerns, and finally, economy. However, in Malaysia, we know that the cost is always at the top, right? Okay, that's the utmost important in any construction, okay, on soft ground. If it's too expensive, then of course it will not be viable to the construction. Okay. In fact, nowadays PVD seem to be one of the most effective ground treatments that have been employed, okay, in construction on soft ground. Fast, it actually reduce the time of consolidation and you speed up the rate of consolidation. So from say 2 years to 8 or 6 months, and then you achieve 90% consolidation, and then you have an ample platform, okay, a bearing resistance for structures, okay, for buildings, also for roofs. Now, I want to get some idea with everyone here is that we are trying to integrate between the volume change behavior and also buoyancy. So the idea is to use a lightweight material. We talk about settlements. They are basically divided into three phases. Immediate settlement, you have a primary consolidation settlement, okay, consolidation settlement, and then you have the secondary compression. Right? Now, the thing that is always causing problems to us is the consolidation settlement. When we actually build our embankment, okay, we estimate what is the consolidation settlement based on the compression index or based on the coefficient of volume compressibility, it's either CC or MV. And we look into the compression characteristics of the soil, right? And how long it takes for the excess pore water. So we are talking about the development of the excess pore water pressure because hydrostatically the water is there, okay, in the ground, But as you load it, it will generate the excess water pressure, causing a massive effect to the soil. So the dissipation of this excess water pressure reduces the void ratio. So as the void ratio reduces, so you have a volume change, which is settlement. So these are the things that causes a lot of ambiguity in the design and also in the construction. Not only that, after it has experienced 90% consolidation, or you can say 100% primary consolidation, you have another uh, uh, phase, which is termed as secondary compression, where you have the reorientation of the soil particles after you have all the excess water pressure fully dissipated, right? So the thing is, the soil is always dynamically in motion. It experiences a slow rate of settlement after it has experienced 100% conservation. And this is where, after construction, uh, you will see that sometimes think it is already stabilized, but a few years you can see that the ground, the apron of the building, and then the surrounding ground starts to settle, and you will see that the building or the structure is already uplifted. But basically, when the building is on piles, a set of piles, uh, it is static, and the ground is slowly experiencing settlement. So when you are talking about Terzaghi and Froelic's theory, okay, they are limited, okay, during the time to basically discover the process of consolidation. So, based on Terzaghi and Froelic, right, if it is an ideal case of consolidation, they assume the soil to be homogeneous and fully saturated, and the volume change occurs in one dimension based on the direction of the stress applied. So it actually limits the movement of the soil as you load. Okay, it experiences only vertical movement, so it is confined in the lateral direction. And then you have Darcy's law of water applies, and if it's a two-way drainage, you have top and also bottom drainage, right? And then, of course, the coefficient of permeability and the volume compressibility remains constant, right? We maintain the compression characteristics and also the coefficient permeability, okay, as it consolidates. And the change in volume corresponds to the change in void ratio, where the ratio between the change in stress and the change in void ratio remain constant. So these are the limitations that Terzaghi and Froelich came out with, to basically simplify the process of consolidation. Now, with the enhanced technological features that we have nowadays, right? You can actually do an advanced test. Okay, you can measure it on site. You can also look into not only vertical consolidation but also lateral compression of the soil, the lateral movement of the soil. So, in in a way, Terzaghi synthesized that on a big scale of the embankment, he only takes a small sample underneath the embankment. So from that small sample, he has deduced these five aspects of limitation so that they can come out with the theory of consolidation. So the best thing about this theory of consolidation is that it is the removal of excess pore water pressure generated from the additional loading, right? So got me thinking of how are we going to look into further improvement, integrating buoyancy, because buoyancy, if you look at ships, okay, you look at barge, look at this lightweight mats, okay, they float on water, and you apply load, and it still floats. Right? So how do you want to integrate buoyancy with solidation? So basically, the concept of buoyancy was introduced by Archimedes in 250 BC, and he stated that any object totally or partially immersed in fluid is buoyed up by the force equal to the weight of the fluid displaced by the object. Okay, so our Professor Chen, together with his team, okay, provides an example of flotation mechanism of the pipe, okay, where the buoyant force of a structure is governed by the Archimedes principle, equivalent to the displaced volume of water when the structure is immersed, and then is multiplied by the unit weight of water. So here's the concept. Okay, you have a fluid that exerts a net upward force on any object surrounds. Okay, here, all right. So you have that. Okay, that is the buoyant force. So the force is due to the increased pressure at the bottom of the object compared to the top. Right? So you have that force acting at the bottom, which stabilizes the lightweight material. Okay, if you consider a cube with sides L, okay, the buoyancy force is equals to F2 minus the force acting downwards to the material, which is equals to the rho of water times the gravitational acceleration times the volume of the material. So, the fraction of an object that is submerged when it is floating depends on the densities of the object and the fluid. So your submerged volume, or solid of volume Ps and density Os, floating, okay, in a fluid of density Os. So you have that volume submerged equals to volume of soil times the density of soil over density of fluid, right? Okay. So interesting thing is, how is it going to be integrated in consolidation? Sometimes wonder, right? Uh, you have an embankment, the ground, you have the soil, you have fully submerged, loaded, experience settlement, right? And when you experience settlement, right, you have a displacement of water, which is the excess pore water pressure is basically dissipating, going back to hydrostatic water level. Now, the thing is, when you talk about consolidation, it is basically removal of excess pore water. It's not removal of water. If you're removing the water is still there in the ground, right? So it is a removal of the excess pore water pressure that is generated from the load. Right? Now, in the case of buoyancy, so Archimedes principles, the buoyant force, okay, equal to the weight of displaced fluid by object, right? So F PU is equals to FB, okay, taking the FPU as the PU foam, right? And you have that generated, and FPU is equals to FP, which is 3 kilonewton. So how to make the PU fully submerged below the groundwater table? So you have to add in load, right? So the load there plus with the 6.81 because the uh, initially the buoyancy force is 9.81 kilonewtons per pressure is kilonewtons per meter squared. So you need force of well 3 9.81 minus 3 to actually have the foam fully submerged in water. So the additional load would be 6.81 kilonewtons, right? And this has been verified from the compressive strength test, okay, using the consolidation test using the CRS test on different thickness of the PU foam. Right. So how do you get that into saturated soft clay? Say you have 1 meter PU foam in stiff clay. So the PU frame is placed below the ground level. And to ensure the PU foam is placed below the ground level in saturated soft clay, first condition, okay, so you have to do a test, right? So it's proven from the CRX test, okay, for stiff clay and also for soft clay. So this is the result from the calculation. So you have the buoyancy force must be more than the FTU, which is the force from the polyurethane for uplift to occur. So to prevent from uplift, okay, so you have to apply a load P. So that is where you have the buoyancy force 9.81, okay, minus the FTU, which is the load from the PU foam. Okay, so you have additional of 6.81 kilonewton. So if more than 6.81 kilonewton load is applied, that means you have vertical displacement, right? Okay, this has been also verified using numerical simulations and also laboratory tests, right? And during the time of this research, we have conducted also a buoyancy test in Rowe. Okay, the buoyancy test, and for your information, you know that water is incompressible, right? So it's incompressible. So you have basically the bulk stiffness of water of about 2.2 gigapascal, whereas the stiffness of the soil varies, okay, from soft to stiff between 1 MPa, say about 100 MPa, okay. That is the we call that hard soil, right? So these are the basic stiffness of the soil that you can imagine ranging from there. And the bulk stiffness of water is more than the soil. That is fairly interesting. So we look at the theory of consolidation. Now, the thing is, in consolidation, right, for initial stress, they've used this, Tazagi have introduced this spring, piston and spring analogy, right? So you have a spring as the stiffness of the soil, right, and then you have water. So as you load onto the spring, right, and water, it will actually generate excess pore water pressure. So when you open the valve, allow the water to actually dissipate, okay, it will cause volume change. Okay. That means it will cause settlement. And at this time, the pore water pressure, the excess pore water pressure, start to decrease or dissipate. So when it goes back to hydrostatic pore water pressure, the ideal condition of the Zagi is that there will be no more settlement. Okay, so it's achieved 100% consolidation. Okay, so you would have settlement anymore. But in reality, after the soil has experienced primary consolidation, there is the secondary compression, where basically the settlement still occurs, but at a minimum rate, where the reorientation of the soil particles or rearrangement of the soil particles occur. Okay? Now, this is in, we say, saturated clay. But if you're talking about peat soil, they have another phase, which is termed as tertiary compression, where it is due to the um, disintegration of the organic material in the peat. That's the problem with peat soil. It's always compressing, okay? And it has very extremely high moisture content, right? The moisture content is more than the solid body, right? So to make things easier, we want to understand the concept of consolidation. So we take a clay layer, okay, at the center, with a thickness H, and then you have sand layer at the top and the bottom. So this sand layer acts as a drainage path for water to flow. And presumably, this is a one-dimensional consolidation. So we are putting it in a audiometer, uh, audiometer casing, right? So a specimen of 20 mm height, 50 mm in diameter. Okay, so initially, as you load that, okay, you have a total stress increase, right? Okay, this is the graph of total stress increase. Okay, against the depth, right? and then pore water pressure increase, and then effective stress increase. So as you load it, what will happen is that, okay, load, it will actually generate excess pore water pressure at the center of the clay layer like this. Can all the participants see my arrow actually? If not, can just Dr. Aswani, can you see my arrow slide here?
Yes.
Yes. Okay. Right. So as you load, right, it will generate the excess water pressure at the center of the clay layer, and at the top and bottom, it is presumed that the water dissipates immediately because you have the sand layer, so it immediately generates the effective stress increase at the top and bottom. But once the water, excess pore water has fully dissipated, excess, yeah, not the hydrostatic pressure, pore water pressure, is excess pore pressure. Once it's fully dissipated, you have a effective stress increase in the soil. So that is the theory of consolidation. So with that, the theory, then we've come up with a lightweight material to actually address this problem. So one of the lightweight material that I use, okay, for construction, okay, for rehabilitation, is the polyurethane foam. Well, it's either a single part or a two-part polymer, and it's within the carbamate group, and it is referred to as the urethane groups in the backbone of the structure. Okay, when it is two-part, it is a reaction between this isocyanate, which is an isocyanate part A, together with the microglycol, which is known as the polyol, or with a combination of microglycol with chain glycol acid. To easily understand it, is that the isocyanate part A is the hardening agent, whereas the microglycol or the polyol is the expansive agent. So you mix that together, okay, with a certain ratio, you will get this PU foam expanding almost 10 to 20 times of its liquid volume. So this is where it actually reduces the cost of the works and also the injection part. So basically, I have introduced this polyurethane foam injection system for rapid ground repair and remediation without excavation and replacement. So you did not have a very big excavation. Basically, repair the subgrade. Okay, we can just inject, and then it will restabilize the subgrade by increasing as it expands. It recompacts and it increases the density of the soil. So it densifies the soil without applying additional overburden pressure to the foundation soil because it is lightweight, right? So the objective of the system is actually to remediate and also rehabilitate problematic soil by injecting lightweight polyurethane foam at high pressures using the hydraulic power packs into the weakened soil. So what is the hydraulic power packs? And you can see there is this mobile equipment here. Okay, you have this part A and part B being put in a bucket, and it's mixed together as you inject it into the ground. Okay, so it actually has a mixing head, okay, at the joint of the injection rod. Okay, right. So basically, this foam, they have two types. One is the hydrophobic type, and the other one is hydrophilic. Now, hydrophilic polyurethane is basically not suitable for ground repair. But if you want it to plug the area where you have a lot of moisture or water, right, or you have like um, capillary rise, okay, you can use hydrophilic polyurethane, okay, because when it is in contact with water, okay, it will expand up to 5 to 7 times from its original liquid volume with the cis of the moisture, okay, where you have water content. However, for ground repair, we use the hydrophobic type, which actually expels water, right? And the rate of expansion is between 6 to 20 times from its liquid volume. Based on my experience, when we want to eject in the ground, okay, with loose material, it will expand up to 10 times. And when it is voided underneath pile embankment or slab, then it will expand approximately up to 15 times from its liquid volume. Okay, so you et al. Refers hydrophobic polyurethane as foam where it has an accelerator to control the curing time. And the advantage of using this foam is that it can expel water during expansion before it stabilizes the soil. And the polyurethane is basically a lightweight material with high insulation quality, high expansion rate, and quick reaction time. So it expands between 5 to 10 minutes and then it starts to cure. The curing time is between 3 hours to 24 hours. Once it hardens, okay, you have sufficient strength, sufficient resistance, it is lightweight and becomes solid. Okay, it is basically an inert material, right? And when it expands, actually it generates heat. So it has exothermic reaction during the expansion, right? So can we have a video played here by the organizer? For Naisha, is it? Polyurethane foam, right? Okay, back to my screen. So, from the emergence of PU foam injection system as one of the alternative methods to solve ground settlement issues and rehabilitation of existing superstructures and infrastructure, so we thought that we want to introduce something of like an EPS type, okay? Instead of you have EPS blocks, we introduce flatbed, or you can say mattress, right? A polyurethane flatbed, okay, to reduce the overburden pressure for the new construction of the embankments and platforms. At the same time, we want to introduce buoyancy, okay, to reduce the effect of settlement on soft saturated deposits. Therefore, the idea of integrating consolidation and buoyancy is the key, is a key in the designing and also construction of the PU flatbed, okay, to support the platform above it and also provide buoyancy. Therefore, it reduces the effect of consolidation settlement. So the objective is actually to provide buoyancy effect and to reduce the overburden pressure. Hence, you reduce the amount of settlement of soft ground. So in addition, this lightweight properties will help to reduce the development of excess water pressure, where it in turns become buoyant force to support the lightweight material. So instead of the excess pore water pressure dissipating, okay, laterally anywhere in the soil, okay, it will basically transfer as a buoyant force to support the lightweight material. Okay, so here is the concept. Okay, so you have, let's say, a soft foundation deposit. You excavate, and then you place the geotextile separator, wrap it. Okay, you place the PU flatbed, and then you wrap it, fill it, and then you construct your roof. Okay. Now, can you play video number 4, one Aisha? Then play video number 2. Okay, this is how it's being placed on the excavated area. You can see it is very lightweight. Okay, you can arrange it. Mm. So it's actually quick. When we did this, about 50 meters long, okay, it took them only about 4 days, okay, together with the gluing. Okay, so you take a concrete block, it's quite difficult to handle with this size. It's lightweight. It's only about around 80 to 150 kilograms per cubic. Okay, can you play the second video where you have the gluing? Okay? We will stick all the panels together as you glue that, right? Okay, so basically, how do we want to actually design this now? Uh, so I consider this idea, with the team, the research team, and also with the PhD students. So we come up with the idea, right? uh, when we want to design the PU flatbed, we take into account the effect of consolidation and buoyancy. Okay, so the consolidation settlement equation basically was modified, right, to integrate the buoyancy effect of the PU flatbed. Hence, the pore pressure due to the PU flatbed, U HPU, is introduced. And since the lightweight block is introduced, the existing hydrostatic pressure U naught is also taken into consideration. So, initially, when we calculate for consolidation, um, the bottom variable here is actually sigma naught prime, which is the effective stress of the soil, where considers consolidation whereby the water dissipates as you consolidate. But in this case, when you introduce a lightweight material, okay, you have that hydrostatic pressure initially there. It's like water. You're putting something on top of water, then it floats, right? Put a barge on top of water, it floats. Then you put sand a little bit on top of water, it still floats, partially submerged, but it still floats. So what is actually holding it down? Okay, sorry, it's holding it, not holding it down, it's holding it up. What is resisting it from submerging? So it's basically presumed to be the hydrostatic pressure, okay, as well. So, since the soft ground is assumed to be fully saturated, the term of initial effective vertical stress, which is this bottom variable here, is substituted to initial total vertical stress, which is sigma v naught, sigma naught, which is uh, sigma prime naught plus with the pore water, hydrostatic pore water pressure, U naught. Okay. So this is the three consolidation equation that we have modified. For OCR equals to 1, okay, this is the standard Terzaghi equation. When it's OCR more than 1, but the loading is less than the pre-consolidated pressure, okay, this is the equation. And if the OCR is more than 1 and the additional total stress is more than the pre-consolidated pressure, okay, so this is the equation. So this modified equation was observed in the consolidation test using Rowe cell and the buoyancy test in a Rowe cell with the inclusion of PU flatbed models at different thicknesses. So you can see there's a PU foam layer here, okay, this model. So that is the schematics of the consolidation of the Rowe cell, okay. Best thing about Rowe cell is that you can measure the pore water pressure, okay, the top and also bottom, right? So the top and also the bottom. This one is the cell pressure, okay? Cell pressure, the water generate on top of the rubber membrane, okay? However, in the design, of course, we talk about buoyancy. One thing that is very critical is actually uplift pressure. So if you have inundation, for example, you have flooding, will that PU uplift and, of course, destroy the whole embankment? So we must have a counter counterweight, a sufficient counterweight to hold the PU in place. So in the proposed design consideration, the buoyancy force and the uplift pressure are to be calculated to ascertain the initial condition and fluctuations of the groundwater table or flooding if a situation occurs. The thing that really worries me is not settlement anymore, is the uplifting, okay, uplift. And one project that we had experienced, okay, in MPPE chemicals, where we installed the PU injection, right? The year that we installed the PU injection, uh, Pahang was hit by a very tremendous flood, right? So the whole of Kuantan almost becomes submerged. So I was afraid that the PU foam, where we injected at MTBE, would also uplift all the gas pipes, okay, in the MTBE. And of course, fortunately, it does not, because it has sufficient counterweights, not only from the field but also from the concrete sleeper itself to cater for the uplifting. Because we have recorded the settlement, okay, is between 2 mm. Sorry, the uplift is between 2 mm and the settlement is 2 to 4 mm. So I say, all right, uh, should be okay. Right? So this is the test that we've conducted, Russell apparatus. This one, we did a buoyancy test where we put in only water and also a PU with material on top. So we run a buoyancy test. We want to see the compressibility of water, okay, because water is incompressible. So I'll show you the data later. And then the other one is the CRS test, right? And you have inclusion of PU foam and the soil. Okay. In the row cell as well, we also did soil sample and also PU, okay, sandwich between the sample and also the loading diaphragm. It is the loading diaphragm, right? So this is the testing material. You can see two parts of the PU form. Okay, you have the tea color is the polyol, and the black color, which is the coffee color, is the isocyanate. So mix that together, actually agitate it, and then start to expand within 5 to 10 minutes. Then you have to wait for half to 1 hour for it to cure at 2/3 of the strength. and you want to wait for it to fully cure is after 24 hours. So basically, we did the consolidation test and buoyancy test, okay, in the row cell to control the distribution of pore water pressure during the consolidation and volume changes in the cell during the test. So in a row cell, the test sample is loaded hydraulically by the water pressure acting on a flexible diaphragm, what I've just shown you just now in the diagram. Yeah, and the drainage of sample can be controlled. Hence, you can measure the pore water pressure, right? Okay, back pressure is applied to basically simulate the in situ soil condition. And this test, okay, on the loading follows similarly to the odometer apparatus, whereby each load is applied constantly for about 24 hours. So we observe the displacement and also the changes in the pore water pressure. So as the excess pore water pressure dissipates, okay, it becomes constant, then we can apply a second loading stage, right? Okay, this is how we mix it. Mix the two, and then wait for it to expand, and then we cut it, okay, nicely so that we can fix into the row cell. Okay, this is the, if it's water, then we fill it, we fill water and then we put it on top. If it is soil, then we put the PU foam on top of the soil, right? Similarly, this is what is being done in a constant rate strain test. Okay, we put that. Okay, unfortunately, this one has some difficulties in making it cylindrical, right? Then place it on top, and then we put in the load cap, and then we run the test. Okay, so material properties, you can see this is a different sizes of the PU, okay, cylindrical sample, okay, with a different ratio, 1 to 0 0.5, 0 0.25 to 1, and then 0.75 to 1, right? And we did the UCT test, okay, to determine the different variation of the mix. So this is the uh, scanning electron microscope of the polyurethane foam. You can see this is the polyurethane foam. Okay, you have a lot of voids. And then the inclusion of the polyurethane foam together with the soil. Doesn't look uh, different, but you can see you have this layer of soil and then you have the foam. Okay, voided, actually filling the voids in between the soil particles. So we did this material test, right? And we had different range of mix, and finally we got the compressive strength. Okay, uh, and then these are the ratios that we try to adopt. Okay, because at site sometimes if the mix is of the isocyanate is more, then it is rigid. Okay, if you have more expensive agent, like for example, you have two polyol, okay, uh, in essence to um, isocyanate, so it becomes flexible with stiffness of about 15 MPa. Okay, not so bad. Okay, so hence we summarize the properties of the foam, right? So you have 0.8 to 1.5 is the unit weight, okay, between 80 to 150 kilograms per cubic, and then stiffness modulus, right, 15,000 to 60,500, and then the Poisson's ratio, compressive strength, okay, between 240 to 2,300 kPa, right, and then its permeability. Okay, this is the test that we have already conducted in the uh, row cell. Okay, we consolidation test. This one is buoyancy test. You can see PU thickness as it becomes thicker, you have less uh, displacement. Okay, so this is already uplift. Whereas on soil, you can see thicker the foam, okay, the lesser the displacement, right? Okay, and then here, okay, you have loads and then you have settlement with different thickness, okay, of the PU foam. This is without the PU foam. You can see the displacement is more than 20 mm, right? And then if you introduce a lightweight material, okay, it reduces significantly to 10, even to 7 mm, right? So there's a drastic change as the thickness increases, right? So how we do this on site? Okay, this is one of the test site. Um, Basically, it's in Cebu, Jalan Lapangan Terbang. Yeah, I think about kilometer 800. Okay, chainage 800, not kilometer 800. Chainage 800. So you have uh, that area is badly uh, experiencing undulation and also rutting. So we excavate that, okay, to about 1 meter, and then we basically need to introduce a trench to when you have water filling in this excavation. So you have a trench there so that the water could actually flow out from the construction site, right? And then we roll that area, make it smooth so that we can have a flat surface to lay our geotextile, and then we arrange our PU flatbed, okay, and then we glue it. Once it becomes one homogeneous panel, a very big uh, panel, right? PU mattress or flatbed, then we backfill and compact it. And then, of course, we resurface it. Later, I will show you the product of this work. Okay. Now, this is a small scale test that we've done in Polytechnic Sultan Idris Shah in Sabak Benam. Initially, this is the ground, this is the walkway of Persis. You can see the stump is already exposed, right? And then we excavated it, and then we treat it with PU flatbed about 1 meter from the surface, right? Now it is very nice, okay, to walk on. And just recently, I had a student who was previously doing her diploma in Persis into 2021. So I asked her whether this area has settled a lot after we have actually done this in 2017 or 2018, like that. And she said, "Oh, well, I think it's okay. There's no settlement. Okay, the walkway is level, right?" So we actually have the data. I will show you later on. We did a 6 months after we had treated that particular area. We have repaired that area. So we actually monitor settlement for 6 months, right? So these are the settlement points. Okay, that is the temporary benchmark that that we fix on top, right? And then that is the walkway to the hotel kitchen. That is the walkway, which is this one here. This one is near the swimming pool, right? And we did leveling, right? Procedure. Okay, there we install markers, right? Settlement markers, and we measure using the digital level, and that is the result of the settlement after 6 months. Okay, we did that basically into 2018 after it has been constructed, and we monitor settlement, and after 6 months it's roughly about 10 millimeters, so roughly about 1.2, 1.3 mm, okay, in 1 month. right? So this is the profile. Okay, settlement marker 1, 2, 3, 4. Of course, 1 basically should not settle because it's on fixed platform. Okay, it's on piles, right? So you have that profile, and then this one is at the swimming pool. Okay, that is at the swimming pool. Okay, supposedly it should not be uplifted. This is the settlement marker where settlement marker 5, which is actually on the rigid platform, supposedly not to experience uplift. But this one here, you can see, okay, it only settles less than 10 mm. So I would say it works, right? Well, it's an alternative. You can use it, but if the fact that it is not suitable for construction or for application, then you can resort to other alternatives. Okay, other method of uh, ground improvement technique. Okay, so based on that sediment monitoring, you can see that the maximum sediment recorded on the walkway, okay, was about 8.1 meters at the walkway, and by the swimming pool is about 11 meters, adjacent to the hotel kitchen after 6 months. So average between 1.35 meter per month and 1.83 millimeter per month, respectively, for both locations, right? So if you look at that, the sediment value is gradually increasing at the walkway adjacent to the swimming pool, and the profile for different sediment marker locations showed difference of about 0.4 mm at the final reading. Okay. So the settlement is said to be uniform throughout the walkway, and it is still within the tolerable limits. All right. So as for the walkway adjacent to the hotel kitchen, the settlement profile for different settlement marker locations show average difference of 1.97 meters at the final reading. However, there is a slight sagging to the walkway due to these differences, but it is unnoticeable visually. Okay, you cannot see it visually, but you can actually see that from the monitoring data, right? Okay, this is Jalan Lapangan Terbang Sibu. Okay, another test site. Okay, we did, okay, in Cebu, right? It's very bad. Okay, you can see that is the existing condition. You have undulation, cracks, and also rutting. So we excavate that, provide a trench, and smooth ruling, lay the geotex, and then lay the U flatbed. And after arranging it, you glue it, and then it becomes one homogeneous flatbed. Okay, about 50 by 7 meters. Very nice, right? And then later we backfill this, and then we place the crusher eye, and then we compact it to the specified density, and then we surface the bitumen so that you have the pavement on top of it. And finally, this is the product. Okay, this is the site visit after 14th June 2020. We did that in 2018. Yeah, 2018, 2019, right? So we did that, and this is the condition of the pavement after 2 years. And this is after 3 years. Okay, still intact. And I just came back from Cebu last week. And we went onto this area. So we have a smooth ride on top of that pavement. But once the PU section ended, the road becomes uneven. It's very interesting. So we requested to fix that area, but of course, the budget has to come from the owner of the road, and also it has to come from the concession. So they actually provide us with another site for us to do our repair. Okay. Okay. This is the proposed research location. Okay, is at Jalan Kampung Paya Redan, Melaka, and you can see that is our engineer Samsul Amri holding the PU flatbed, and this PU flatbed is about 400 mm thick, right? 400 mm thick, with a width of 50 mm. Why we split it into 500 mm width? Because it's easier to handle. If it's 1 meter by 1 meter, it's quite heavy with its PU itself for for an individual to handle. But you can have 2 or 3 people to actually carry it. It's quite mobile in terms of its weight. Then we actually wrap it, right? And then we fill it. Right, this is the side. Okay, we put it actually at the transition section between the pile embankment and also the earth embankment. The other side is maintained using the transition slab. Okay, so this one we use the PU flatbed. So we monitor that. There's a series of monitoring settlement instruments, okay, for us to observe, right? And we did a finite element simulation. Okay, we take the soil properties and then the PU flatbed properties as well. You can see here, right? Okay, we are using the advanced soil models, okay, for the field, having soil model, and then for the soft soil, we use the soft soil CREaTE model, right? And this is the results of the simulation. So with no treatment, okay, immediately after construction, you have 95.10, okay, 0.1 mm, and then after 5 years, it is more than 250 mm, right? And then we also observe the lateral movement from the construction, from the simulation as well. Right? So that is the excess water pressure developed, and finally, this is the stability of the embankment. Okay, 5 years post construction. So we introduced different thickness of PU. And initially we used 400 mm PU flatbed because the contractor says, the supplier say that is actually the cheapest. Of course, you have 200 mm is the cheapest of most of it, but the optimum design is actually the 400 mm thick flatbed. So we did the simulation, and interestingly, the settlement has reduced significantly. Okay, from 259 is only about 199.73. So that is about 60 mm reduction. And then you can see the pore water pressure dissipation has also reduced. Yeah, sorry, the development of excess water pressure has reduced because the previous 3 kPa has become the uplift pressure, right? And then you have increased stability, about 1.947, right? So these are the settlement simulation, okay? And I would like to actually thank my master student. At the time, he was doing his dissertation, and I was at that time also attached with JKR CKG. So we basically had a heavy discussion on how to run this simulation. Okay, it's very proactive. Okay, and that is the results from the deformation. Okay, so then we install that at Jalan Kampung Paya Redan. Okay, that is the pile embankment. This is the PU flatbed. Okay, then we glue that, and then we wrap it with the separator. Okay, can you play video 6, please? Okay.
Potong. Potong kek tu. Bisa tajam tu.
Jadi semua tak ada potong? Dah.
Bayar dia sikit.
Okay. Okay. So that is the installation at Jalan Kampung Paya Redan. That is the section where we have our PU flatbed. And then they resurface it. And then that is the monitoring result. Now, interestingly, the settlement is maximum is at 40 mm, but the lowest is actually at about 70. Okay, for settlement marker set on the right hand side. On the left hand side, because it's close to a channel, so possibly you have wetting at the side of the construction. Whereas if you look at the other side where you have the transition slab, supposedly it should not settle, but then it settles about maximum of 20 mm, right? Which is quite similar to the section where we had our PU flatbed. So basically, supposedly the transition slab should not settle as much as the PU flatbed. So it seems that if you swap this transition slab with PU flatbed, it works similarly to the transition slab. But since it's lighter than the slab, so you might have an uplifting once you move past through it, and then it becomes back to its original position because of its lightweight capabilities, and actually it reduces the effect of vibration. Okay, so the thing is, this PU flatbed, okay, is patterned under JKR CREaTE. So the usage of this is rather limited because you need the approval of JKR and UITF to actually use this product. So we have come out with another system which we call geopolymattress. Now, it's also lightweight, but the beauty of this geopolymattress is that it is a polyurethane foam coated expanded polystyrene system. So it is lighter and it is nicer. In a way, it looks very nice, okay, when it is foam, right? And then, of course, the objective is the same, okay? And we want to actually reduce the effect of uh, settlement, okay, by introducing the buoyant force. And this is the design configuration of the geopolymattress, okay? And then there's the method of construction. And we were given a project at SIBO again. And this is actually a very bad surface, okay? It is undulating, okay? Because of the undulating causes cracks and also potholes. And you have that longitudinal cracks, okay? And then you have that uh, diagonal cracks. Oh, it's very critical. So what we did was we excavate that area, lay again geotex, and then we place the geopolymattress. Of course, we glue it, and then we wrap with the um, geotextile separator. Okay, and then we resurface it, compact it, and then form its final pavement level to the final surface and road marking. And after 2 months, this is the road. Okay, so they had a smooth ride instead of bumpy at the section, you have undulation, and I just came back from there, so we did ride along this road, and so far I did not experience additional settlement. Okay, okay. This is at Jalan Kampung Pulau Betong. So you want to show that it is really lightweight, so we placed it on the ground, partly filled with water, and when the water rises, okay, this whole PU uplifted. So what happened was they had to put in the NJB to hold down the PU foam as a counterweight, so that later, once it has been installed, then we can cast the RC slab counterweight, because the fill is quite low. And this section is 1.5 meter going up to 2.2. So we had our 0.4 meter thick of the PU flatbed, sorry, geopoly mattress. And then we have about a 300 thick of the slab for the counterweight, so that it would not cause any uplift, okay? Or you won't have the uplift due to the fluctuation of the groundwater. Okay, and we have verification test for that lah. Okay, we did cube test. So this is the strength, and that is the test conducted on a real sample, right? Okay, that's PU, that not a a wood block. It's a PU foam. You have the PU foam, okay, encapsulating the EPS inside. Okay, so finally, that's the conclusion. Oh, okay. Hopefully, we can finish this on time, right? So the strength of the field has increased, and the field has been rehabilitated to ensure that the volume change of the molecular soil or settlement can be reduced. And the compressivity characteristics have also improved significantly. So the lightweight capability shows that the PU flatbed provides additional buoyancy to reduce the effect of primary settlement. Hence, you minimize the dissipation of excess pore water pressure, and since the pore water pressure becomes the buoyant force, right? So, because we are using the hydrophobic type, so it is water resistant. Therefore, the PU flatbed provides a discontinuous layer between the fill and the foundation soil. And the fill material provides counterbalance to the uplift pressure from the fluctuation of the water table. Therefore, there is no need of a concrete slab to act as a counterbalance to the uplifting of the PU flatbed if the fill thickness is sufficient. If it's insufficient, that is where we need to design the counterweight slab, right? And the work provisions are quite simple, easily mobilized. You reduce the time of construction, cost of additional construction material, and mobilization and transportation, right? Of course, you have temporary disruption of the road. Now, since you, for that 50 by 7 meters, you only install it within, say, a week. The most the time taken is actually from the excavation and also the surface construction, okay, the reconstruction of the pavement. So what are the benefits, right? So shorter remediation time. You can actually place constructed material less than 2 weeks, depending on the size of the project. And then after that, the traffic can be opened immediately after the pavement has been reinstated. So you can have, it is high compressive strength and buoyant. Therefore, it is resistant to additional or excessive load. Addition, the rigid characteristic partially absorbs vibration to the rehabilitated ground. So initially, if say you have voids underneath the pile, embankment, or approach slab, can fill it with this PU flatbed, or you put an EPS and then you spray the PU to cover the EPS, right? So it becomes a geopoly mattress, and then it actually reduces the vibration initially experienced when you have voids underneath. So when you have reduction in vibration, so you have less disruption to your structure. Okay, and then lightweight, so it reduces the likelihood of primary settlement or further subsidence and maintains the existing overburden pressure to the foundation swab. So you don't add additional overburden to the ground. And finally, it is a low permeability characteristics of the material, hence it reduces the chance of water infiltration. Right. Okay. So these are some of the references you can look up. Okay, you can look me up as well. I have a few papers there that I've introduced a PU foam injection system, and also with my PhD student, my master students, and also my undergraduate students. They have been working uh, so much to so much to actually assist this research, and well, I would like to actually thank them a lot. Okay, for this idea to be implemented in the field, and of course, as I mentioned, we are, as academicians, not only we want to produce engineering graduates, but we also want to assist the industry to actually solve their problems. So I would actually like to thank so many individuals and people that have assisted me with this research and the usage of this lightweight material. So it is very interesting to work with so many, valuable individuals. So they have given, like for example, um, my postgrad postgraduate master students, okay, Mr. Wafi and Mr. Imran, okay, working. Imran is working on the buoyancy test, and Wafi is doing on the consolidation test with by integrating the buoyancy, right? And then I have my uh, colleague, previously was my PhD student, Dr. Diana, and then my mentor himself, okay, Engineer Bahadim Baru, right? And then so many people involved, okay? Dato Ismail Abdul Rahman, and also uh, Engineer Shamsul Amri, and not to forget Professor Dr. Azmi and Assistant Professor Dr. Muhammad Jamaluddin. Okay, so they have all assisted in doing this research work, and I do also have engineers from CREaTE, okay, Mrs. Nurul Ilmi, and Ika Kusmawati from JKR, and also Nagendran as well. Right. So with that, I thank you all very much for listening to my presentation. Thank you.
Okay, thank you, Dr. Isma Jayadi, for your presentation. So I would like to open the session for Q&A. So there are several questions in the list. Some of the participant is requesting on your presentation slide. Is it possible to give them?
Oh, okay. First of all, I would like to apologize to all the participants here. Some of this presentation are quite PNC, so I could not actually share these slides. But I mean, you can feel free to look at it. But this one is quite I would say private and confidential to some of the collaborators as well. So I'm so sorry I could not share the slides with everyone here.
Okay, so sorry about that. If you have any question, maybe you can directly ask Dr. Isma Jayadi. Yeah? Okay,
Yes, you can contact me.
Yeah, you can contact directly. Okay, there are a few questions. One question, I start with the first question from Mr. Cairo. He asked that is PU flatbed has some kind of shrinkage over time?
Okay, Dr. Azwani, can you repeat the question,
Yeah.
because it's not
Okay,
clear
sorry.
just now.
Okay, not clear. Okay, he asking whether the PU flatbed has some kind of shrinkage over time.
Well, we did actually store it exposed, and so far we do not experience shrinkage. But there were actually problems in terms of arson because what happened was there are basically we are working on one particular site and then it is being we rented the place. What happened was they actually wanted to burn the geopolymeters, and they managed to actually burn it with by putting kerosene. If you want to burn it in freely, it's quite difficult because it is rather resistant to fire, right? But we tried burning it, it becomes just totally black. But of course, it slightly weakens the foam's intrinsic behavior. But to basically burn it all through, you have to put kerosene, and we do not actually experience shrinkage when we expose it on site. And we had one site that we have done previously 2 or 3 years ago. We had the foam on site that is already brought back to the storage area, and so far I do not see any shrinkage of that material on site. Okay.
Okay, all right. Next question from Engineer Lim. He's asking what are the differences between EPS blocks and polyurethane blocks?
Okay. What difference between these EPS blocks and polyurethane blocks? Okay. When you talk about EPS, these EPS blocks, they are compressed from beads of smaller, lightweight polystyrene, right? And then it forms the EPS block. And you can easily peel it off. But PU blocks, they are inert. They are formed. They become a uh, uh, solid body or material. Material, okay, becomes a solid block, and you have actually difficulties in peeling it. Okay, you have to actually cut the PU blocks so that to form shapes, right? So it's fairly different from EPS blocks. And okay, basically there is a video that I forgot to ask the organizers to play. All right, the organizers, can you play the video where you have a 10-ton compactor moving on top of the PU flatbed? Okay, so you see this is a 10-ton compactor, right? That is the PU flatbed. So we've taken partly the curved one, right? Then you can see, okay, you can hear the cracking sound. But then, you see the compactor
Terus jalan.
riding on top of the
Terus.
flatbed.
Terus habis ke je?
Jalan habis.
Habis kan? Nanti naik balik.
Ambil gambar dulu.
Ha.
Jalan habis tengok macam mana.
Okay. Sorry, you have to turn your head. View
Okay.
this video.
Dia pecah sebab dia tak stable.
Dia pecah sebab dia tak mesti dia
Kalau
kosong.
rasa okey.
Tapi dia taklah kata apa? Kemek terus kan?
Patah ni dia.
There you can see. It only breaks at the edge. The whole PU form is rather intact, but we take call this the defected one. Okay, we took the defected one. We didn't take the flat one. So if you take the flat one, probably you won't have that break. Okay, the cracks or the breakage at the edges of the U flatbed. Okay, Mr. Lim, does that answer your question?
Okay. Right, next question from Engineer. Hold on. Okay, Engineer asking about this. There's one question from Engineer asking, given the very low permeability of soft clays, do you have actual measurements to prove that your foam expansion in the ground really expel water from within the soft clay to reduce its water content and thereby compacted it convincingly, like you said? How much reduction water content in the compacted soft clay did you find?
Okay, thank you, Mr. Yi. This is quite an interesting question. Okay, yes. Basically, when if we use the injection procedure, we have to use a higher pressure to cause hydrofracturing within the clay so that we could remove the water or the voids, the water in the voids by introducing the hydrofracturing. Okay, so we basically reduce the moisture content up to about 20 to 25%, and we basically have strengthened. Well, to say the compressibility characteristic is still maintained, the CC value is still maintained. We reduce the void ratio from zero. There's a test that we did from 0.8 to about 0.6, and of course, since the PU is lightweight, so it basically does not induce additional overburden to the soft clay. Yeah? And basically, you reduce that void ratio by around 23, 24%, like that. Okay.
Okay. There's another
Okay.
question also
See.
from Okay, Engineer Yi also asking another question. If you had used a layer of 200mm thick PU blocks to form a slab inside an earth-filled embankment, you have only omitted an earth loading to the ground of roughly equivalent to the weight of the 200 mm soil per earth thickness, corresponding to the thickness which the foam had replaced. So, the physics behind the PU foam slab application should be loading reduction on the ground surface rather than being akin to the phenomenon of buoyancy in water. Therefore, shouldn't reduction in embankment settlement simply be the result of reduced loading onto the ground of soft clay?
Okay. There's another interesting question. Engineering has so many, knowledge on fundamentals on this. Yeah. Well, basically, when you introduce the lightweight material, yeah, you have partly reduce the fill height. Okay. You have less reduction on the ground surface. Okay. However, uh, the thing that actually interests me is that when you introduce a thick, about 200 thick, you have to calculate what is the buoyancy force acting towards um, the lightweight material is one thing, and then what is the overburden, and finally you have to introduce the hydrostatic water level as well. Okay, where basically now in you run in a real life situation, the excess pore water pressure would actually dissipate, right? But then the hydrostatic pressure, the level is still there. So we have introduced not only the effective stress of the soil, but also the generated of the hydrostatic water pressure underneath the PU flatbed of that 200 mm thick to basically support it as a buoyancy force, additional hydrostatic pressure, and also you have that overburden with less weight. The thing is, 200 mm thick is well, it's a rather thin in compared to the field. So we introduce a slightly thicker foam. Well, it is twice of that. It's 400 mm, and so far it works. It works well with the design process and also on the buoyancy effect to the ground. Okay.
Okay. Next question from engineer side intros. Why such cost and technically effective method is not used nationwide? Still under trial project. Dr. Ismail, can you
I'm
get
reading the question.
oh, okay. Okay.
Okay, thank you, Engineer Sahid, for the question. Now, we actually had a few projects that we have done with JKR, okay, mostly on rural roads, not on the not on urban, not on highways. Okay, mostly the PU flatbed is on rural roads. But on highways, we resort to PU foam injection system because the PU foam injection system is basically less destructive in terms of PU flatbed because PU foam, we only need to inject at the location where you have problems at the approach embankment and also at the area where you experience transition differential settlement at the transition, and also in some root areas where you have undulation weaken of the subgrade. So we inject that so that you only have minimal disruption to the road service. That means you only close the TMP only during the working hours. After the injection, you can actually open the traffic. So the cost of using PU injection is actually cheaper in comparison to the PU flatbed. Well, for the PU injection, we had a lot of projects in SKVE highways. We have also in JKR projects, in some areas on FT002, the bridge approach at Bukit Raja, and then we have a few more at culverts at Hutan Melintang, Jalan Jerangau Jabu. So we had a lot of PU injection projects surrounding. But the PU flatbed, initially, we had it for research in JKR projects only in Paya Redan. And then later, we got the opportunity to actually work in Cebu. So we have a few PU flatbeds installed in Cebu, in Jalan Oya Lama and then in Jalan Lapangan Terbang Cebu. And in fact, in Jalan Oya Lama, we had two sites there. And then, of course, the other one is the Jalan Kampung Paya Redan. Basically, the PU flatbed only emerged in roughly about 2020, 2019. At that time, we were still doing that research and we finalized that. It's just recently adopted.
Okay. Next question from engineer Ting. Singkong asking about PU. He asking about, has PU flatbed been used in the road construction at deep pit condition?
Okay. At deep pit condition, well, we actually did that in Jalan Oya Lama. Basically, it's on big soil, but the Jalan Lapangan Terbang, Cebu, the pit thickness is roughly about 15 to 20 meters. But then we placed it on top of it. We had to excavate, and then we fill it on top of that.
Okay, next question from Mr. Liu. What is the testing or sampling frequency required for the PU installation? Any test required for the glue?
Okay, wait. Where's the question, Dr. Azang?
I
Question
repeat
from
again, from Mr. Liu.
yeah, it's not appearing in the question.
Oh, okay.
Yeah.
You want me to read the question or you can read yourself?
Oh yeah. Okay then. Right. So
The
what is
from
the
Mr. Liu. Yeah.
application
Okay.
required for the
Yeah,
PU
for the PU
installation
installation. Yes.
and
Any
any
test
tests
required
required for the glue? Okay. Now basically the glue is PU itself. So we have to form it we have to form it as a cube, and then we do a cube test. And for sampling frequency, usually we at one site that we did for Jalan Kampung Pulau Betong, we had 3 specimens, okay, tested, right? So supposedly we wanted to have more, but fortunately, it's not specified in the contract. So if it was me, I would like to specify more than say about 5 to 10 units, okay, per 100 meters roughly. But of course, this one it goes back to the contribution to the construction costs for testing material. So we usually limit between 3 to 5 specimens per 100 meters.
Okay. Next question from Engineer Yi again.
Ah,
Okay, he asked about pit. A pit permanently submerged in water should not disintegrate. So why should there be tertiary consolidation in such ground unless the groundwater table is depressed to leave the material exposed to aeration or oxidation?
okay. Uh, so why should there be tertiary consolidation in such ground unless
Yeah.
groundwater table is
Water
depressed
table.
to leave the material exposed to aeration or oxidation? I would not say I'm not an expert in peat soil, but there are also cases. It is submerged in water, but then the moisture content is very high. I think there are records almost 1,000% moisture content, and you only have it's either fibrous, hemic, or septic, and mostly the fibers they dissolve, right? They dissolve, so it could actually cause abrupt changes to the volume of the peat. So that is probably uh, well the case for fibrous peat. I would not say tertiary consolidation would not occur. Well, it might occur because of that the disintegration of the fibrous material in water, right? Possibly, but of course, you see, I'm not an expert in peat soil. So I think should request to have I think Dr. Hazwani has a better answer because she is also doing peat soil.
Okay. Yeah, normally when exposed, they asking about why there should be tertiary consolidation in such unless the groundwater table is depressed with material. Yeah, because when it's exposed to the air, it's easily degraded. So when it's easily degraded, then there might be tertiary consolidation will occur compared to when the soil is the peat is submerged in water. That's the idea. Okay. Okay. Mr. Khairul. Okay, asking about can I get estimated cost per meter squared for the PU flatbed?
Okay. Right. Uh, you want to get the estimated cost? I think this one on the commercial side, I would actually leave to my collaborator to get in touch with you. So you might want to get in touch with my collaborator, which is Geocon they have a rate for different sizes of the PU foam. At the moment, we are using the 400 thick. Well, it would not cost fairly much. I think it's the other day for per meter is roughly about, I think about between 700 to 900 ringgit. But I think you want the actual estimated cost, you can get contact, or you can contact my collaborator for further information.
Okay. Engineer Pui asking about asking you to share some relevant papers on your work instead of the presentation material. Is it possible?
Well, here, Mr. Engineer Pui, I do have a few here published from Dr. Diana and myself. Okay, the study of buoyancy behavior using consolidate tests. Okay, I think Engineer Pui can take a picture of this, and then from my postgraduate student, my master student from Nur Hibatu Wafi, and also one Muhammad Imran. Okay, this consolidation statement and buoyancy behavior. And then, of course, another thing, and again, from Dr. Diana, okay, uplift and settlement prediction model. And then, we have some more down here. Uh, uh, Consolidation integrated buoyancy, okay, ground improvement. And of course, the paper that I presented in the conference, the GE's conference, right? It's also there for you to have a look, right?
Okay.
And most of the papers, they are more onto polyurethane foam injections.
Okay. Next question from Isabel. She is asking about the Cebu site. For the Cebu site, is it clay as the subsoil condition? Does PU work on pit as Cebu? As Cebu has a lot of pit as well, does PU work on pit?
Okay, thank you, Miss Isabel, for the question. Actually, on the Cebu site is actually on peat. So the subsoil condition, the one we work with is on peat, because the road embankment experience a lot of undulation and differential settlement. So we actually did some work on peat soil. The one in Jalan Oyalama is not peat. It is, I think, on the soft clay. But the one at Jalan Lapangan Terbang, that one is actually on peat soil.
Okay, next question from Mr. Tay. What is the lifespan of the material?
Okay, thank you, Mr. Tay. We work with this material, and so far that I noticed, it can, because it is polymer based, it can withstand about 100 years. But in Europe, they recorded about 120 years. In Japan, actually, they had this foam installed or injected behind the bridge abutment in 1980s. And when they excavated, I think recently in 2010, they see that the foam is still intact. Uh, well, when it is polymeric base in the ground, you can withstand quite some time. Uh, the most that we experienced, because it started in 20, 2012, so I think it's now has been 10 years in its service life. That's my experience. Siti.
Okay. Next question from Mr. Muhammad Khairi. Hi, doctor. How long does the flatbed last before requiring to be replaced?
Uh, well, it's quite difficult to answer on how long does the flatbed to actually last. Well, we have installed it in the ground, and I mean, in Cebu, we did came back after 3 months, and we excavated the area because they found out that on the road shoulder, uh, they had a lot of depression on the slow lane. So when we actually went there to excavate, we made a trench to look at the PU. It is still intact. So I would say it would last quite a long time, as I mentioned to Mr. Tay, probably between 100 years, because I've been working with the PU form for more than 10 years now, and most of the sites we did not actually come back to do the injection. And in the SKVE, when we install, we spray the PU form, and then we did uh, break the surface of the concrete to look at the PU, the geopolymeters. It's still intact after 2 years. So I think you need not require maintenance.
Okay, right. Next question. Isabel asking about whether do you provide courses on PLAXIS. So what is the best way to reach you?
Ah, of course, Mrs. Abel. Yes, we do actually have uh, courses on Plexis. I actually did a few training with the consultant. Yeah, you can contact me directly, or well, Dr. Nohazwani is also one of my representative. So we can get her to also organize a full course here in UITM. Not a problem, because in our master's program, we have a geotechnical numerical modeling course where we actually introduce the students to use Plaxis and Slope W. So we actually explored the Plaxis on more onto the advanced soil models. So if you're, if you're happy, you can come and contact me personally, or you can get can contact Dr. Hazwani. She's also one of the representative uh, for the course, right?
Okay, next question. Let me check. Okay, from Engineer Pui, looks like it is mainly used for repair job. Uh, it's relating to your PU, Risma. Is it due to cost preventing it from becoming the basic construction material?
Okay, thank you, Mr. Pui, Engineer Pui. Now, actually, the one that we had in Jalan Kampung Pulau Betong in Penang, that is actually a new site. So the problem with that site is actually they had a culvert crossing, and they wanted to have pile embankment on top of the culvert crossing, okay, to reduce the effect of overburden pressure, direct overburden direct contact onto the culvert. So then the cost was quite expensive. So then they resort to an alternative method of using the geopolymeters. So we actually designed the geopolymeters to cater that problem by putting it on top of the uh, culvert, the crossing culvert crossing, and it basically reduced the effect of direct overburden contact. And since it is partly flexible, so the foam actually absorbs vibration. So when it absorbs vibration, it reduces the direct contact to the crossing culvert. So that project in Jalan Kampung Paya Redan is actually one of the new projects that we introduced the geopolymeters.
Okay, next question from Engineer Chai. He said that your PU is a solution for treatment of deep pit soil more than 6 meters in depth. He asking whether it's applicable for construction of rigid pavement or building floor steps.
Yeah, thank you, Mr. Engineer Chai. This is quite interesting because if you want to use, as a lightweight support to the existing structure, well, you can resort to using this geopolymeters. In fact, some of the projects, when there are voids underneath the rigid pavement or the floor slabs, we fill in the geopolymeters. We fill it in. We put the EPS block and then we spray it. So when we spray that, we basically reduce the effect of vibration coming from the slab contact to the ground, because initially when there are voids, okay, the slab will vibrate intensely. So when we introduce that cushion, it's like a cushion. Okay, you introduce the geopolymeters, becomes a cushion, and actually it supports the rigid structure. Right. So you are talking about a deep pit soil. Okay, you want to introduce the EPS underneath the building. Well, it is partly a recommendation. I wouldn't say it's the best solution, but you can actually resort to this solution, you know, and you reduce a lot of one thing, fact of settlement, additional settlement from the ground, and it is actually also reducing vibration uh, from the slab contact, okay, from the loading above.
Okay, next question from Miss Anis. Can this PU flatbed be used for house construction?
Mm, okay. Where's the question? Dr. Azwani?
Okay, I repeat. Can this PU flatbed be used for house construction?
Based on my experience, I haven't tested it yet. As yet, I haven't tested it as yet. But if you want to use it as as a rib underneath the rib slab, you want to provide cushioning or reduce the effect of settlement, so providing buoyancy. I think you can resort to using for house construction, but of course, everything need to be tested. So you have to have the bold and guts to do it, right? Because one thing about creativity and innovation, you don't limit the ideas of doing it. You have to try, and then of course you will expect it to solve your problem, or it will fail. But if you expect it positively, then it will be positive. But if you expect it to fail, then of course it won't work. But as far as I'm concerned, most of the work that I did was all experimented. It's all experimentation, or basically opportunities for me to come and solve the problem. So so far, alhamdulillah, it works for me lah. But I'm not sure if it works for the others. Right?
Okay, next question from Mr. Omar Khairi. Are you able to share the rough estimate of cost per meter square of pavement? Is it cheaper compared to standard flexible pavement?
Right, of pavement, if it's cheaper compared to standard pavement. Okay. Well, I wouldn't say we use this for um. You're talking about the standard flexible pavement structure. Well, I would say well, the costs would be slightly higher compared to the one using a standard flexible pavement. But it depends on the condition of the ground, right? If you are looking into firm subgrade layer, so you would not need to use the PU flatbed or the geopolymeters. But if the ground is very weak, you have very weak foundation soil where you need to have uh, a lot of treatment, okay, whether you had to use chemical stabilization or you want to have PVDs or whatnot, using PU geopolymeters would actually reduce the cost by about 20 to 30%. That is my rough estimate.
Okay, next question from Engineer Chai. How much is the cost saving by applying this method of ground foundation treatment as compared to piling and suspension slabs construction?
That to pile, okay, piling and suspension slab construction. Well, in terms of piling, I would say compared to piling, this one is cheaper probably. But for suspension slab construction, it depends on the material that you use. If you're talking about the probably the precast slab, it will be cheaper than the geopolymeters. Because geopolymeters, I would say it's rather expensive. However, for difficult grounds or based on the construction, because the installation is fast, and then the construction method is basically has reduced a lot in terms of the services. So talking about material wise is expensive, but if you're talking about the cost of construction, this would be slightly cheaper than doing piling and also suspension slabs, because piling you need a lot of big machines, okay, to pile down to the set depth. But using a PU, you have cast it on site or you cast it in the factory, and then you just transport it and then you just lay it. So the cost of construction in terms of laying it is rather cheap. Then you just glue it. In comparison to suspension slabs construction, you need big machines to prepare the formwork and then the reinforcement. So the cost would basically be much higher than just installation of the geopolymeters.
Okay, last question for the day from Engineer Lee again. In asking, the foundation ground with in situ watt ratio of 0.8 that you mentioned, you measured to have reduced to the final watt ratio of 0.6 after foam expansion or hydraulic fracturing was unlikely to have been soft clay. That would be fairly well compacted soil. Is this correct?
Uh, I wouldn't say well compacted, Mr. Yi. I think you can say it's firm clay because you've taken the sample which has experienced consolidation 20 or 30 years ago, because it is actually on at I remember the site. It's one of the plus highway. It's already experienced consolidation for a long time. So we've taken the sample and then it is without the PU. I would say it's firm. It's not soft. So it's not soft or very soft. It's just firm clay. So you have that the void ratio between of 0.8 within 0.8 to 0.7 like that. But then because of the moisture content, I think about 60% like that. So we need to have the hydrofracturing. So we inject it at high pressure. I think the highest pressure that we did was about 1,200 psi. It almost causes uplifting to the concrete pavement.
Okay, I think that's the end of the question for today. So I would like to thank Dr. Isma for his knowledge sharing. So if you have more questions, you can directly ask Dr. Isma regarding his research. Dr. Isma would like to share anything before we stop the session.
Dr. Azwani, you are
Yes.
breaking up.
Oh yeah, I'm wondering before we stop the session, would you like to say anything to the participants?
Hello, Dr. Azwani. We can't hear you.
Yeah, sorry.
You are breaking up.
I think my internet is having problem with my connection. Okay.
Okay.
Okay. So we already achieved. We already reached the end of the session. So before we leave, do you have anything to say to the participants before we end the session?
Okay. First and foremost, I would like to thank IEM for this great opportunity to present this research work, research product, where we conduct this to basically solve the industrial problem. Not only doing research in the university, but also to provide solution to the industry as well, and to get connected with industry and find what are the ambiguities and anomalies that probably we could work together. And secondly, I would like to thank everyone here that has participated in this webinar and giving a lot of good questions, posed a lot of interesting questions that has also triggered some ideas and also knowledge enhancement towards this research product. So thank you, everyone, and I bid everyone good luck in your future undertakings.
Okay, with that we end the session. Thank you.